Perfect.
Okay, so first, we will start with a review of the theorems of circles. We have learned many theorems. The first one, so about the circles. Mm,
Wait, I think my camera angle isn't right.
It's fine.
Trying to fix it. Yeah.
Okay, so give 2 points. You can connect them because this a chord, a segment. And we connect them to the center, this angle. Okay, let's check. Aaron, what's the term for this angle?
Angle O.
Uh, so we have a name for this. One for this one for this angle.
Wait, which one?
This one.
I forgot.
Uh-huh. Amy, okay, two choices. Okay, yes, Amy, you want to say something?
Oh, it's like, okay, yeah, I don't remember.
Okay.
It's the angle where all three of them are equal, right? If you can.
Well, not there yet. First, what is called? It's called the central angle.
Oh yeah.
Okay.
Wait. Yes, that one.
Mm-hmm. We pick another point called P. We connect PA. Oops. Connect PB. Make it straight. Kira, what about this angle? What's the name for this? This
I
one. Uh-huh.
I only remember the central angle. I don't remember this.
Okay. It's called the inscribed. Inscribed.
Wait, may I go to the bathroom?
Yeah, be quick.
See.
Okay. So it's not easy to remember this because you don't understand what this inscribed means. Inscribed is inside the circle and with a point on the circle. Later we will learn more about inscribed object, inscribed triangle, inscribed circle, a lot of inscribed stuff, inscribed angle here. So our first theorem is a very important theorem. Jessica, can you hear me, Jessica?
Yes.
Okay, turn on the camera. What does this theorem tell us? What's the inscribed angle theorem? Okay, so it tells us this inscribed angle is half of the corresponding central angle. Half of the central angle. So let's say this angle is fixed, but this angle, the inscribed angle, changes if we shift the points along the circle. If we move it to there, to a new point, we call it Q. This AQB is another inscribed angle. The theorem also applies to this angle, so we have the same characterization. AQB is also half of the central angle. Now, both angles equal to the half of the same angle. These two angles must be the same. So a consequence of the theorem is it tells us the inscribed angle is independent of this point as long as it does not cross A and B. This is a very important theorem, even though it's very simple. It plays the same role as what we had in the algebra, like 1 + 1 equals 2. We will use this very often. It's like we use this in algebra. We use this for many theorems about circles. Okay, we'll start with one very interesting application. Start with a general case and then a special case. The quadrilateral. We can consider the summation of the angles of the opposite angles. In the general case, summation could be large or could be small. But if we consider a cyclic quadrilateral, that means all 4 points are on the same circle. It's called okay. Let's draw a circle and pick 4 points. Arbitrary 4 points. I pick this one.
Is that E?
Where?
Cyclic?
You mean here?
Yeah.
Cyclic. Just C. 3 C's.
Okay.
C. Call them A, B, C, D. Connect this. Now you can see this is a cyclic quadrilateral. The special property of this cyclic quadrilateral is the summation of the opposite angles. We call it the here. Angle BAD. Go BCD is 180 degrees. Angle ABC. Okay, so this is called the opposite angle theorem. If we add these 2 angles, in a general case, we don't know what we have. We could have something large, could have something small, but in the cyclic quadrilateral, the summation of the 2 opposite angles always 180. The summation of this of 2 opposite angles always 180. Okay. Now let's recall the interior angle theorem for quadrilateral. What's the total summation of the interior angles? Amy, do you remember this one?
360.
So summation of the 4 angles equals 360 degrees. If we can prove this one, the second one follows from the interior angle theorem. So we only need to prove one of them. Okay, let's check the first one. How to prove this? I will mark the center. BAD. Connect. Okay. So we have this angle BCD, angle BOD. What's the connection between these 2 angles? Amy, what do you see?
they're like corresponding almost.
Okay, so they correspond to the same chords. We can apply
Yeah.
the Inscribed Angle Theorem. This is the inscribed angle. This is the corresponding central angle. So this is the half of this one. Okay, so proof by the Inscribed Angle Theorem. Angle BCD. Uh, I'm going to call this angle 1. Okay. Then by the same reasoning, this is another inscribed angle. The corresponding central angle is complete, is this one. I'm going to call this angle 2. Angle BAD. Okay. This one may be not that easy to see. If you not believe this, you can divide this into 2 parts and check them separately. So this also holds, but you can and you can check this. Okay, check. Okay, next I'm going to add the 2 angles. Okay, now let's check what's the summation of these 2 angles. Aaron, angle 1 and angle 2.
Let's see, it's called 360 degrees.
Okay. Okay. So
That
this will
makes
be
BCD plus BID 360 too.
so this is the total angle. This will be 360, which will one half maybe 180. So this completes the proof of the first equation.
Mhm.
That means the summation of the 2 opposite angles of a cyclic quadrilateral always 180 degrees. The summation of these 2 is also 180 degrees. So this application of our inscribed angle theorem. Next, we'll consider the intersecting chords theorem. So let me draw another circle. Find the 2 chords, they're intersecting. I label this A and B, C and D. Give an intersection point. Then the intersecting chord theorem states that the product of these two segments equal to the product of these two segments. It's not easy to prove this directly, but the equivalent form, if we convert the product to two quotients, this one, AECE, correspond to this side, BEDE, this side. So that's separate. This is the same as we wanted to prove that the products are the same. It's sufficient to prove the quotients are the same. If we can prove this, we take a cross multiplication AEBE, good CEDE, we get our equation. And this two give us a hint how to prove it is similar triangles. Okay. For the two triangles, triangle ACE, triangle DB, angle 1 equals angle 2, angle 3 equals angle 4. Okay, Kira, I claim angle 1 and angle 2 have the same measure. Is there reason for this?
Wait.
Why?
If like the triangles are similar, then it would be the corresponding.
Okay, so we wanted to prove that they are similar, but we
Oh.
don't know yet. Aaron, how could you conclude the two angles have same measure?
Because angle 3 and angle 4 are what do you call it?
Let's start with angle 1 and angle 2.
Oh. Angle 1 and angle 2.
Mm-hmm.
They're similar because hold up. Right. They are inscribed angles.
Okay, they are the inscribed angles for the same chord AD. Then by our inscribed angle theorem, the inscribed angles are the same no matter where the point is. So in particular, this is the inscribed angle, this inscribed angle for the same chord, they must be the same. Okay. Amy, what about 3 and 4? Why are they the same?
They're vertical angles.
Okay, they are vertical angles. Now we apply the AA similarity theorem. We conclude the two triangles are similar. From there, we see that the corresponding sides have the same ratio. AECE, DEBE. You can see to prove theorems about the circles, we use a lot of the result we have about triangles. So this is about the chords. The next one about tangent line. Tangent line intersect the circle at one point. Okay, nice. So if we call this point P a point outside of the circle in exactly one point, we call this A. We will call this point the tangent point. Now we find the center. So the tangent line theorem. Okay. So the theorem, if this line is tangent to the circle at this point, then this must be perpendicular. Very useful result. Both angles are 90 degrees. Okay. And next, we have a tangent and a chord. In particular, have a tangent chord angle. We have tangent point A found on the line P and a chord B. We call this angle the tangent chord angle. And the Tangent-Chord Theorem is that the and the tangent chord angle is also half of the central angle. Okay. Okay, let's think about how did we prove this one. Fred, can you hear us, Fred? Okay. Why? This angle must be half of this angle. Fred, what do you think? Why this must be half of this one? Aaron, do you remember how we proved this one? Not so easy. This a little bit involved. Okay, so to prove that this is the half, I will mark the midpoint. And connect this. Okay, so a proof. Connect O and the midpoint. AB. Okay, I claim the two triangles OAM triangles OB are congruent. Okay, let's see why. Why the two triangles are congruent? What theorem can we apply for congruent triangles?
Let's see now.
Mm-hmm.
SS similarity theorem, I'm guessing.
Okay, which size?
Huh?
Kira,
Are we
how
trying
to
to,
apply?
are we proving that they're similar or that they're congruent?
Congruent.
So then it'll be SAS.
How do so SAS? Which side? Which angle? Which side?
The middle like OM, because that's a shared side, and then AM
Okay,
and BM and the yeah,
there's a midpoint. Okay, same length.
and then the two angles between like O, yeah, between those two sides, OMA and OMB.
Why are they the same?
Um, don't
Okay, that's what we want. After we prove that they are congruent, we will conclude these two angles are the same, then each must be 90 degrees. Okay, that's what we want. Okay, Aaron, we have two. What's the third condition?
For the SAS?
SSS.
Oh, SSS?
Uh,
Third condition.
1, 2.
And 3, which is O and OB.
Why are they the same?
Because OM and AM and BM are the same, if you can prove that.
So because both are the radius of the circle. Kira, is that what you want to say? Okay, because both are radius. Okay, so this by the
Well, technically, if you extend the M to the circle point, then that's radius. But yeah, that's technically what I meant.
okay. I'm not good. So this one is shared, so it has same length. Because this midpoint same length, the radius same length by the SSS theorem. Okay, so we skip that. From this, we conclude the two angles. Angle OMA, angle OMB. And these two angles are supplementary. So each to progress. This is 90 degrees. Then the summation of these two angles also 90 degrees. It implies angle OAM, angle AOM is 90. Why? What theorem did we apply for this one?
The intersecting chord thingy.
No. No. So we know this one is 90. Why the summation of these two must be 90? Amy, guesses?
It's like complementary, right?
Okay, there are different ways to prove this. The direct one is the interior angle theorem. Do you remember that theorem?
But it's like the interior of a triangle is like 180, right? So if that one's 90, then the other two added together have to be 90.
Oh yes, so this is the interior angle theorem. Let me check the message. Okay, cool. Okay, Samuel, got it. Okay, so now let's check another summation. Compare OAM angle M, that is angle BAP. What's the summation of these two angles? Kira, guesses?
90.
Why?
Because of the tangent theorem, like
Okay.
the yeah, like
Uh-huh.
from the center point to the tangent point is perpendicular to the tangent line.
Okay, so by the tangent line theorem, this is perpendicular to the line. So summation of these two angles is also 90 degrees. Okay, so these two angles, we add the same thing, get the same thing. The two must be the same. Okay, then the two triangles are congruent. These two angles must be the same. So this will be half of the sum. So the tangent chord angle is half of the central angle. So to prove this, we use the SSS theorem about congruent triangles. We check these two angles must be 90 degrees. These two angles are the same, and they add to 90 degrees. They add to 90 degrees, so these two must be the same. Okay, several steps. Let's check the picture, you know how to prove this. Okay.
Wait, can let me write that
Yes,
this
yes.
down.
Okay, let's have 5 minutes break. We will resume at 8:20. So 5 minutes break.
Okay.
Okay. So this is the tangent-chord theorem. This angle, tangent-chord angle equals half of the central angle. If we combine this with the inscribed angle theorem, you can see that this tangent-chord angle is the same as the inscribed angle. We can add one more piece to this. Angle BAP. Angle. Oh, too many p's. Let's use a different letter. Let's call this Q. So two ways to interpret this tangent-chord theorem. This tangent-chord angle is half of the central angle and also equals to the inscribed angle. Next theorem is about a tangent and a secant. Again, let's draw a circle. I'm going to draw a tangent. I will draw another line. Okay. We call this one a tangent. Or a tangent line. We call this one a secant. A secant line. Secant means cut. You can see this line cut the circle into two parts. A cut line. Then the tangent-secant theorem. We call this P. This tangent point A to intersecting points B and C. To show that why they are the same. Again, we will convert this to quotients. Convert it to quotients, then they will be related to similar triangles. This is equivalent to so PAB is this triangle. PAC, this triangle, so two triangles. I wanted to say PAB, PCA. What theorem could we apply? And how to apply this? Why these two triangles, PAB and PCA, why are they similar? Jessica, why are these two triangles similar? What theorem do you apply?
The tangent-segment theorem.
Okay, we will need that. Okay, so we will need that theorem. You want to check these two angles. Okay, so this is a tangent line, a chord. This is the tangent chord angle, angle PAB. By our tangent chord theorem, this tangent chord angle equals to the inscribed angle of the same chord. So this is the chord, and this is corresponding inscribed angle. So by that theorem, angle PCA by the tangent chord theorem. Okay, these two triangles also share the common angle at the P. From this two, I conclude the two triangles are similar. Can you tell me why? What theorem do we apply in this step? Aaron. From here to similar triangles. Why? By which theorem?
AA similarity, I think.
A similarity theorem. To conclude, PAB, PCA, the corresponding sides have the same ratio. PA, PB. So first, second, first, third, first, second, first, third, PCPA. Okay, so then we take a cross multiplication, we get what we want. So that's the Tangent-Secant theorem. Then a simple application of this theorem give us the Secant-Secant theorem, intersecting secant theorem. Okay. Okay, I'm going to draw a circle.
Mm.
And we'll draw two secant.
Mm.
One, okay, two. I will label the points A, B, C, D. The theorem now becomes PA, PB, PC, PD. Okay. There are different ways to prove this. A direct way is to check the two triangles are similar. An indirect way, we can apply this theorem twice. So to apply this theorem, we will draw a tangent line so that we can apply this theorem. I'm going to draw a tangent line. For this one, I'm going to label this as Q. Okay, so by the Tangent-Secant theorem, PQ squared equals to PA and PB, also equals to PC and PD. So by the previous theorem, Tangent-Secant theorem. Again, Tangent-Secant theorem. So if we combine the two, we get okay. So this is the intersecting secant theorem. So two different proofs. One direct proof, similar triangle. I skip it, but you should be able to fill in the details. But indirect proof will apply the tangent-secant theorem twice. First time PQ and P, this one, tangent-secant. Second time, tangent-secant. So the product have equal to same square, so they must be the same. Okay, so these theorems, we use triangle theorems to prove circle theorems. Next, we're going to go the other way. We show that circles are also related to triangle theorems. Okay, for that purpose, we will consider a notation called concurrency. A new term, okay, what does this mean? If we draw two lines, they will intersect as long as they're not parallel. Okay, that's the easy case. Okay, let's consider what happens if we draw a third line. If they are not parallel, in general, it could be something like this. It intersects at two different points. But a special case is when the third line goes through the intersecting point. This we call it concurrent. Okay. So that's our notation, 3 lines. Concurrent. They intersect at a single common point. So this point is known as the point of concurrence. Okay, a new notation. 3 lines, we call them concurrent if they all intersect at a single common point. This point, we call it the point of concurrency. It's a very special situation. In general, we would expect they intersect at different points. Okay. Now the for triangles, let me draw a triangle. Has been a while. Okay, not that. A, B, C. Okay, first let's recall one of our homework question. It asks to draw the angle bisector. Who remember this? The angle bisector. Jessica, do you remember this one? Angle bisectors. No? Okay, that's fine. Amy, what about you?
I don't know.
Okay, so as the name indicates, the angle bisector is a line bisect the angle, so divide the angle into even parts. Okay, so about equal. Oh, it's not equal. Let me adjust. Okay, it's about equal. Without any knowledge, if we want to draw the angle bisector, is it possible we draw it like this, or we draw it like this? But that's not accurate. The theorem we're going to introduce, that we have proved in our homework, is that if we connect this line, this bisect this angle.
Wait, is
Yes.
it so it's in circle? I mean, in center.
Yes. So
Okay.
we're not there yet, but that's what we are going to. Where we are
Okay.
going to. So it's a very important theorem. So let's read theorem. Let A, B, C be a triangle. Not bad, you're right. The three angle bisectors are concurrent. That means the three angle bisectors intersect at a single common point. Let's recall how we proved this theorem. So this is maybe the homework from 2 weeks ago or 3 weeks, I forgot. We draw the perpendicular lines from this point. We showed that these two triangles congruent. So these two sides equal length. These two triangles congruent, these two sides equal length. So they also have the equal length, equal length. So these two angles must be the same. Okay, so this line bisect angle BAC. So the proof fruit.
Excuse me.
Mm-hmm.
One of the people in the meeting just left.
Uh-huh.
I just wanted to say.
Okay, yes. So it's Samuel. Okay. Okay, Eric.
Hi.
Hi. When did you just arrived?
Yeah.
Okay. So this point we call it the in-center. Right? So we defined a new relation between lines. We call them concurrent if they intersect at the same point, not at three different points. So this common point, we call it the point of concurrence. Okay. Then we record the theorem we proved in our homework that the three angle bisectors intersect at a common point. So we say that they are concurrent. So this point of concurrency, we will call it the in-center. What that means if we draw the perpendicular lines, okay, we call this D, E, F. This is I. We showed that I, D plus I, E, I, F. If we label this as the radius, we can draw the circle center at I with radius R. And I have to move. Let me see how to move this. Okay, it's not easy to move. I will correct this picture later. Okay, let me make this bigger. Okay, that's not good. Not so good. Okay. We call this in-center. That means if we draw the circle of radius R, it goes through the three tangent points. So this circle, we call it the incircle. Okay, in center, in circle, and we call this R in radius.
Question.
Yes.
Can you say, oh, you already wrote it, never mind. I was gonna ask if ID could also equal R, but you already wrote it.
Okay, okay. Okay, so for any triangle, there's a circle inside the triangle, tangent to all three sides. Because in circle, why it's called in circle? It's a short for the inscribed circle. Okay, so why do we call it in circle? It used to be called the inscribed circle. This is too long. We give a short name for it. In circle. Okay. Some interesting observations from this. If we label the sides of the three sides of the triangle, vertex A, I will label this side lowercase a. Vertex B, this side lowercase b. Vertex C, this side, the opposite side, lowercase c. Okay, let's make the labels. I label this A, B, C. We want to find the size of AE, AF. You know, they are the same. BE, BF, BD, same size. CD, CE. What are they? Okay, want to find AE, AF. What do we know? In our homework, we proved AE equals AF. We also proved BD is BF. CDCE. We want to find the length of all of them. We don't know what they are, so let's label them X, Y, and Z. We will find the three sides of them. So AE, AF, X, X, E, Y, Y, Z. Okay, so from the triangles, this is Y, this is Z. What is Y plus Z? Amy?
Oh,
Okay, Aaron. Okay.
I was gonna say BC.
BC, which is our A. Okay. So let's observe y plus z equals A. Kira, what about x plus z
X plus Z equals B.
equals B? Okay, Jessica, x plus y. Okay, Eric, you want to answer? It's Eric.
C.
X plus y equals C. Now what do we have? We have three unknowns, x, y, z, three equations. Next, so this is the algebra problem. We want to solve the unknowns from the equations. How to find these unknowns? Okay, Eric, any suggestions?
So y plus 2z plus x equals a plus b. So
Okay,
2z
that's a
equals a plus b minus c.
okay. So I will follow the same idea. Instead of adding the two, I add all three of them. See what we get. If we add all three of them, I get 2x, 2y,
I have a question.
yes.
Is this a matrix?
Well, we could use matrix, but that's too advanced. Maybe in the future we will.
So what's the point of writing? Oh, I see now.
Okay, so this is the perimeter, and it's twice of our half perimeter S. So we divide both by 2, we get x plus y. Okay, now we are ready to find x, y, and z. X is S minus y plus z. We look up, y plus z is A. Okay, I will give you a few seconds to think about how to find y and z. Any thoughts? Eric, what would you do?
I'll make it y equals s minus x plus z.
X plus z. What is x plus z?
That's equal to b.
Okay. Amy, what about z?
Z would be x minus x plus y in parentheses,
Mm-hmm.
which
And
is
what?
s minus z.
Okay, so we
I already
find
wrote that.
Let me rewrite this one. It looks strange. I'm not sure what happened. Okay, we can know a little bit more. We find these 3 shorter sides, maybe a 6. Next, we want to find the radius. How do we find this radius? Okay, so let's look at this triangle. Triangle BCI. This triangle, the base is A, the height is the radius. What's the area? Area of this triangle. We have the base and we have the height.
It'll be 1/2 of ID times BC.
So this will be 1/2 AR.
Uh-huh. Wait, can you say ID is radius?
Yes,
Yeah.
ID is the radius. Amy, this triangle CAI. So this is the base. This is the height. What's the area?
B times IE over 2.
Okay, so this will be 1/2. Okay, the left AIB. And Kira, this base height, what's the area?
The area will be like C times, well, 1/2 C times the height.
Mm-hmm.
Right.
1/2 C times radius. If we add all 3 together, we get the area of the big triangle. Okay, now what's the area of the big triangle? There's the formula for that, the Heron formula. What's the Heron formula?
S equals half of the perimeter, and X equals S times S minus A times S minus B times S minus C.
Okay. A. Okay, a little bit algebra. So R is a common factor. If we pull out R, we have 1/2 A. And this is our half perimeter S. So we have the formula RS, the summation of the 3 small triangles equal to the total area of the big triangle. Okay, we divide both sides by S, we get the formula for the radius.
That's complicated.
Okay, slightly complicated.
Yeah.
The good thing about this is, as soon as we have the three sides, we can find the in radius. We can simplify this a little bit. Okay, so the formula for the radius of the inscribed circle, the in radius. So not only you know the formula, you know how we derived this. We find the area of the three small triangles. We add them together, we apply the Heron formula. Okay.
Question.
Yes,
Is that area bisector?
area. No, okay, that's a very good question. But they are not area bisectors. That will be a very different topic. We can next time maybe we'll mention this.
Okay.
Okay.
Wait,
There are a lot of bisectors. This bisector, that bisector, they are all different.
wait, oh wait, no. So that denominator is also square rooted, I see.